Mrs. Cribb, and this is going to be notes about the combined gas law and Dalton's law of partial pressures. So pull out your chapter 10 notes, and you're going to need to go to this section. We should have already finished this question here on the last video. So we're at the combined gas law. So here I just want you to notice a couple things. Let's look at this. This is the combined gas law. If the temperature does not change, I would mark it out. What I have left is P1V1 equals P2V2, and that is Boyle's law. So, because the temperature doesn't change, so we get rid of it on both sides. Okay? Whoops, I need an eraser here. What if the pressure doesn't change? So I'm going to mark out pressure now. Well, now I have V1 over T1 equals V2 over T2. So the pressure doesn't change, and that's Charles' law. So Boyle's law is when the temperature doesn't change. Charles' law is when the pressure doesn't change. All right? Let's get our eraser going. Now, what if the volume doesn't change? Mark out volume. Well, then we have P1V1 over T1 is P2V2 over T2. Well, that's the, I'm sorry, volume is not there. Sorry. Woo. Just P1 over T1 equals P2 over T2. And that's this law. Gay-Lussac, Gay-Lussac, Guy-Lussac law. So this combined gas law contains all of the other gas laws into one gas law. And you know you can use it when you're looking at the question, evaluating the question, and you see that there's two pressures or two volumes and two temperatures. So let's try this question right here. Let me make my thing a little bit smaller. So you need to mark up your question. Please do this. This is a good habit to do. Please do it. I'm begging you to do it like I do it to help you keep things straight, because these are plug and chug questions. A gas has a volume of 3.6 liters, so I put a V on top of that when I circle it. When it's under a pressure of 1.05 atmospheres, so that's a pressure unit, and a temperature of negative 15 degrees, that's a temperature unit. What is the volume? Oh, there's another V at STP. Well, STP stands for standard temperature and pressure. So we have two pressures, two temperatures, and two volumes. So which one of our formulas can we use? Well, it's the combined gas law. P1 over V1 equals P2, sorry, I'm going to write this in a different spot because I'm actually going to, all right, P1 V1 over T1 is P2 V2 over T2. Now I'm doing that because over here I'm going to line them up. Now I'm going to list out, you should list your variables. If you're skipping these steps, guys, and I keep seeing you people, some of the gentlemen particularly, not doing this, and so it hurts you. So V1 is 3.6 liters, and V2, that's the question. T1 is negative 15 degrees Celsius, but there's a problem. Can you divide by 0? No. So you have to change it to kelvins. So I have to add 273 to get to the kelvins. And that is, let me check. So I want to mess up my math here. So 273 minus 15. Minus 15. All right, 258. Good. I had it right. All right, 258 kelvins. So that's T1. And P1 is 1.05 atmospheres. All right, V2 is the question. T2, well, if that's the standard temperature. And what's standard temperature? 0 degrees Celsius or 270 kelvins, 273 kelvins. And then standard pressure is the second pressure. Standard pressure is 1 atm, or anything that's equal to 1 atm. Well, this was in atmospheres here. I want our pressure units to match, so I do need to use 1 atm. All right, now I just have to plug it in and cross multiply to solve for the one variable that's not there. So I'm going to put in the numbers, and I'm going to circle them as I put them in. Okay, hold on one second. Check something. So anyway, P1, What I like to do, and I'm going to do it this case, is circle them as I use them. So P1, put it in that spot. All right. And then this is V1. It's hard to tell. So go look up V1, 3.6 liters. Over T1. Well, T1 is up. There it is, 258 kelvins. P2, 1 atmosphere. V2 is my unknown. And T2 is 273 kelvins. Now see, by doing this, I make sure I've used the right numbers into the right spots and make sure I've used all of them over here. Now, we need to solve this. You need to cross multiply. If you don't, you're going to make mistakes. I promise you. So cross multiply 1.05 atmospheres times 3.6 liters times 273 kelvins is 258 kelvins times 1 atmosphere times V2. Now I get to isolate my variable by dividing both sides by 258 kelvins and 1 atmosphere. And if you don't cross multiply, what's going to happen is you're going to end up dividing by the wrong things and you're not going to get the right answer. And this happens every year. The students who are most confident in math think they can just do it and they make the mistakes. The students who are less confident in their math skills do the process and they don't make the mistakes. So don't make the mistakes, do the process. ATM, ATM, Kelvin and Kelvin, liters is left over. And I'm just going to pull it up real quick and put the answer for you. The answer is 3.9997. The last thing we always have to do is check sig figs. So two significant figures. You always use the significant figures for the measured values. You don't use the significant figures from the standard temperature and pressure because those were not measured. That's a definition. So that's 2 sig figs, 3 sig figs, and this is 3 sig figs. This is the correct number of significant figures because I'm subtracting and you look at place value. So 2 significant figures is what I need. That's the smallest number. So I round to 2 places, 4.0 liters. That's volume 2. Okay? Make sure you understand that before you go on. All right, now we're going to look at Dalton's law of partial pressures, which is really easy. It's just taking all these pressures right here. And there, look, notice this is the container T. We would say the total pressure. So the total pressure of this thing is 550 kilopascals. Well, notice all the little colors. This green gas is 100 pascals. The pink gas is 250. The blue gas is 200. You add that all together and you get the total pressure. So that's all it is. It's taking all the pieces and adding it together to get the final part because now they're all in one container. And this happens because I oftentimes am collecting something over water and I need to subtract out the water. Vapor pressure is the pressure exerted by water molecules on top. So it's like if I have a container and there's liquid water and up here's the vapor, that's the vapor pressure. It exerts pressure over the water, okay? Now we need to use this Dalton's law of partial pressures and vapor pressure when we're doing these kinds of problems. It's a word problem where we're going to collect over water. I'm going to show you something in the Prezi in a moment, but let's look at this. We have a 46 milliliter sample, that's a volume, of oxygen gas is collected over water. Box that. That's an important phrase. At 25 degrees Celsius, that's a temperature. When the atmospheric pressure is 102 kilopascals, that's a pressure. What volume? That's a second volume. Pure oxygen is also important at standard temperature and pressure. So you can see we have a lot of temperatures and pressures and volumes, so we're going to be using the combined gas law again. So V1 is 46 milliliters, and V2 is my question again, what volume? T1 is 25 degrees Celsius, but we got to convert to kelvins because we never divide by 0. So that's 298 kelvins. And P1, well, this one we're going to talk about in a minute. What is T2? The second one, pure oxygen at standard temperature. So the standard temperature is 273 kelvins or 0 Celsius. And standard pressure, STP, well, the P as 1 something. All right, we got the unit they use for pressure here is kilopascals. So I really want my standard pressure to also be in the same unit. So I'm going to go way up here to the top somewhere where I listed all the pressure units for you. There they are. This right here is standard pressure. 1 atmosphere. But anything that equals that is also standard pressure. So 101.3 kilopascals is also standard pressure. So I'm going to use that one so that I don't have to worry about converting. So 101.3 kilopascals. That's what my second pressure is going to be down here. 101.3 kilopascals. I'm doing that because of this. Now, this is not P1. Normally this would be. But since we're collecting something over water, this pressure is the total pressure of the gas. So we have an instance where we're collecting, it's like we're having two of these gases together in our container. We have a container and we've collected some kind of gas, and I'm going to use blue for water, and some kind of water. And we need to subtract out the water to know the pressure of the pure oxygen gas. Well, why is that necessary? Let's look at some pictures from the Prezi. Here's the one with the pressures again. Okay? And this is just showing you, this is actually called a U-tube, how you measure vapor pressure. All right, now this is the picture I want to look at. Whoops. I thought I pointed to it, I didn't. So when we collect something over water, this is what happens. When you do a reaction in a Erlenmeyer flask or some kind of vessel, and the gas forms and it goes up through this tube, and we put it underneath water, and then it bubbles out. Because see, we want to catch the gas. If we just let it bubble out in the air, we're not catching it. So it bubbles through the water, and we catch it up here. And we have, it's called could be either by collecting over water or by water displacement, or you could even say wet gas. All those things are important to remember. If it has water in it somehow, you're going to need to subtract out the water. Listen to my words again. Collected over water by water displacement or a wet gas. So up here, we don't just have this yellow gas. We also have water vapor from here, since it's being bubbled through the water. So to find out the pressure of just the pure gas, I've got to subtract out that water vapor. So in this case, the total pressure is 102 kilopascals. So what's Dalton's law of partial pressures? That the total pressure is equal to the pressure of each individual gas added together. So 102 kilopascals is going to equal the pressure of the oxygen gas that I want plus the pressure of the water vapor. Okay, so I need to be able to subtract out the pressure of this water vapor. Well, in order to do that, I need to look at a reference chart that lists them. So let me pull that up for you. Right, what I did is I went to the student Google Drive to chapter 10, and here is the reference chart. I'm just showing you where it is, but I've also printed them out. Okay, so let's look at this. I'll try to get it a little bigger. All right, notice this part is called water vapor pressure right here. So what I do is I go down to the temperature 25 degrees right here, and I go over to the column that's kilopascals, and it says 3.2. So 3.2 kilopascals is the pressure of water at 25 degrees. So that's what goes in this spot right there. All right, so now 102 kilopascals is going to equal the pressure of the oxygen plus 3.2 kilopascals. So I just got to subtract it out so that the pressure of the oxygen, whoops, is equal to 102 minus 3.2. So it's 98.8. Write this in. 98.8. But I need two significant figures because this only goes down to the ones place. So I've got to end right there. So 99 kilopascals. That's what the real pressure one is. 99 kilopascals. Again, how did I get that? I took the pressure they gave me, which was really the total pressure, and I subtract out the pressure of the water at the temperature that it started out at 25 degrees. Where did I get that number? From the chart. So that's the only complicated portion of this. Now I have everything and I can plug and chug. So P1V1 over T1 is P2V2 over T2. I need to put all my values in. P1, 99 kilopascals. V1, 46 mils. T1, 298 kelvins. P2, 101.3 rather kilopascals. V2 is my unknown, and T2 is 273 kelvins. So now we just need to cross multiply and solve. Notice I cross multiplied. So now I'm just going to divide by 298 kelvins and 101.3 kilopascals. So this goes away. So I just have V2 isolated all by itself. Okay, I'm going to go ahead and pull up my calculator for it this time. All right, so it's 99 times 46 times 273 divided by 298. Divide again by 101.3. Don't multiply by that. You will cause a problem. This might need to be in brackets if that's going to cause you a problem. 41.18. Yeah, remember, it's order of operations. If you have to put this in brackets, do that. But otherwise, divide by this and then divide by this again. Now, significant figures is only 2 because all the measured values only have 2. So it's just 41. And I'm probably talking too loud. 41 milliliters is V2. Okay, what's the deal here? What makes this more hard, more difficult? Collected over water or by water displacement or wet gas, you have to go find the vapor pressure on the chart. I'm trying to see if I can find it again. Yeah, I'm not going to worry about it. Find the vapor pressure on the chart and subtract it from the vapor pressure or from the pressure that's given to you right here in the question. Okay, that's the only thing that makes this more difficult. All right, I hope to see you soon.